Dear student, in this lesson, we will continue our lesson of canonical architectural styles. Now we turn our attention to one of the fundamental styles in software architecture that appears again and again, the pipeline architecture, also known as the pipes and filters architecture. The topology of the pipeline architecture consists of pipes and filters, as illustrated in the figure. The pipes and filters coordinate in a specific fashion, with pipes forming one-way communication between filters, usually in a point-to-point fashion. Pipes in this architecture form the communication channel between filters. Each pipe is typically unidirectional and point-to-point, rather than broadcast, for performance reasons, accepting input from one source and always directing output to another. The payload carried on the pipes may be any data format, but architects favor smaller amounts of data to enable high performance. Filters are self-contained, independent from other filters, and generally stateless. Filters should perform one task only. Four types of filters exist within this architecture style. The first one is producer, the starting point of a process, outbound only, sometimes called the source. The second one is transformer, recognized by functional advocates as a map, accepts input, optionally transforms data, and forwards it to the outbound pipe. Tester accepts input, tests one or more criteria, then optionally produces output, based on the test. Functional programmers will recognize this as similar to reduce, consumers, serving as the termination point for pipeline flow, may persist the final result to a database or display it on a user interface screen. Examples of pipeline architecture are Unix terminal shell languages, such as Bash and ZSH. Besides, the pipeline architecture pattern appears in a variety of applications, especially tasks that facilitate simple, one-way processing. For example, ETL tools, extract, transform, and load, leverage the pipeline architecture as well for the flow and modification of data from one database or data source to another. To illustrate how the pipeline architecture can be used, consider the following illustration, where various service telemetry information is sent from services via streaming to Apache Kafka. The service info capture filter, producer filter, subscribes to the Kafka topic and receives service information. It then sends this captured data to a tester filter called duration filter to determine whether the data captured from Kafka is related to the duration, in milliseconds, of the service request. Notice the separation of concerns between the filters. The service metrics capture filter is only concerned about how to connect to a Kafka topic and receive streaming data, whereas the duration filter is only concerned about qualifying the data and optionally routing it to the next pipe. If the data is related to the duration, in milliseconds, of the service request, then the duration filter passes the data onto the duration calculator transformer filter. Otherwise, it passes it on to the uptime filter tester filter to check if the data is related to uptime metrics. If it is not, then the pipeline ends. The data is of no interest to this particular processing flow. Otherwise, if it is uptime metrics, it then passes the data along to the uptime calculator to calculate the uptime metrics for the service. These transformers then pass the modified data to the database output consumer, which then persists the data in a MongoDB database. This example shows the extensibility properties of the pipeline architecture. A new tester filter could easily be added after the uptime filter to pass the data on to another newly gathered metric, such as the database connection wait time. Now let's consider architecture characteristics ratings. The pipeline architecture style is a technically partitioned architecture due to the partitioning of application logic into filter types, producer, tester, transformer, and consumer. Also, because the pipeline architecture is usually implemented as a monolithic deployment, the architectural quantum is always 1. Overall cost and simplicity combined with modularity are the primary strengths of the pipeline architecture style. Deployability and testability, while only around average, rate slightly higher than the layered architecture due to the level of modularity achieved through filters. Like the layered architecture, overall reliability rates medium, 3 stars, in this architecture style, mostly due to the lack of network traffic, bandwidth, and latency found in most distributed architectures. Elasticity and scalability rate very low, 1 star, for the pipeline architecture, primarily due to monolithic nature. Pipeline architectures don't support fault tolerance due to monolithic deployments and the lack of architectural modularity. If one small part of a pipeline architecture causes an out-of-memory condition to occur, the entire application unit is impacted and crashes.